Okay, so hello everyone. Welcome back to the second scissor mechanism section. So today what we are going to be working on is the loading of these scissor mechanisms. So these particular section now will be actually very similar to what we have in the section 8. So we're going to be dealing with the same two bay scissor mechanism, and but the thing we want to change here is that first the support condition. So the rollers are removed from node 2 and node 3, and instead node 3 will be fully fixed in space. And we're going to apply a load here at the central node. So this is really just like using the system mechanism as a bridge. And as a matter of fact, one of the application scenario of the system mechanism is indeed deployable bridges. So people can use this system mechanism to build deployable bridges that allows people to rapidly evacuate from, let's say, some sort of a hazard, or if a bridge is temporarily disabled, we could use a scissor mechanism bridge to rapidly connect to bank of the river to establish some sort of a temporary traffic connection. So this code would help us to learn how can we set up a loading of the scissor mechanisms. So because most of the code will be very similar, I would like to actually just show them, display them in these side-by-side manner as we go over them. And as you can expect, that there's not a lot of things that's going to be changing at the very beginning, right? When it comes to defining the properties of the bars, the length geometry of these mechanisms, how we set up the nodal coordinates. They're pretty much the same, and I pretty much copy pasted the code from last time to here. Right, so the same visual inspection of the node, the same way of setting up the bar elements that connect different nodes, inspecting it, and also setting up the rotational spring, with the 13th rotational spring being the one that we can use to control the deployment. So scissor mechanism is a 1 degree of freedom mechanism, so we just need to control one angle to control the full deployment process, and that's why we're adding these 13th springs to control it. So we also starting from here, this is actually where we have the difference when you compare section 9 with the section 8. So the loading solver that we pick is different. So this time we're going to be using that Newton-Raphson loading solver. So last time we were using that folding solver, and the folding is triggered using the 3-node rotational spring. So let's compare the support. The first 3 node in the support is changed. In the last time simulation, we have a roller in the node number 2 and number 3, so they are able to move in the x direction, that's 0, but they're not allowed to move in the z direction. But this time, the support is changed to we fix the first node, we fix the second node, and then the third node, excuse me. Third node are fixed, first node are fixed. The second nodes are free to move in the x and the z direction. So that's reflected in the drawings, right? Just pay attention to how the rollers and these fixed connections they are assigned. All right. So that's pretty much all the things that we need to change. And what we're going to be doing is we would just apply a 1 Newton load to the system at the node 2 in the z direction pointing downward. And after that, we try to see what kind of deformed configuration we can get, right? So we break that -1 Newton into 5 0.2 Newton forces. So we've already covered these, how the Newton-Raphson method works. So I don't think we need to repeat too much here. And this is the result. So we find these deformed configuration. This is plotted in a real scale. So we do not scale the deformation large. So as we've already discussed, I told you at the very beginning that the setup is actually quite soft. It's polymeric type of material or softwood stiffness bar that's only 1 centimeter, 1 centimeter, but it actually spans an entire meter long. So it's a pretty soft setup in general. And because of that, we do get pretty big, obvious deformation we can see in the graphs, and that's one of the reasons why we set it up there. But the one cool things, the more fun things we hope to do in this example is how about let's try to deform it. Let's try to actually do some sort of shape morphing, reconfiguration with the scissor mechanism, right? So the scissor mechanism can generate large deformation. That's what makes it cool. And practically, for a system like this, let's say if we want to use it as a bridge, theoretically it has the ability to cross different length, right? They can cross the larger distance if we make these control angle to be very small, right? But then we might wonder, okay, now that the bridge is spanning larger distances, what's the load capacity, right? What kind of stiffness do I get out of a structure in this configuration? Can we figure out a way to solve it? So that's the problem we're gonna try to attack here. So we want to first remove the first load, and then we're gonna change the configuration, deploy this bridge scissor mechanism, some bridge longer, and then reapply the load to see what's the difference in the stiffness we obtained here. So to do that, we're going to need to bring back that particular Newton-Raphson solver we talked about last time, right? The three-node folding solver. Yeah, we're going to change the configuration back to these previous support conditions. So the one thing we need to do in order to wipe out all the previous load information is to use this initialize assembly to just reinitialize the entire system so that we change the deformation, the current U matrix that stores the deformation information of the structure, wipe it out, replace it with a zero deformation matrix so that now everything restart from scratch, right? You don't want to carry a large load while you're deploying this bridge, and typically that's true. When you're loading it, it needs to be properly anchored. During the deployment is when it's usually when this reconfigurable structure is weakest. And so we do that. And this time I'm gonna change the new configuration, the target rotation angle for that 13 rotational spring to be about zero point 0.1 pi. So I want to make this angle, this theta angle here, to be a very thin angle, a small angle, so that this bridge can extend and cover a larger distance. So after that, this is what we've got. It's just like what we got last time, right? The bridge got we changed the configuration after running this Newton-Raphson algorithm. We are able to find a new equilibrium location with this system. It's capable of covering larger distance with this right end of the bridge extending to about 3 meter already. So previously it's 2 meter. And with that, we're going to rerun that Newton-Raphson loading solver. So NR is the class that's associated with the previous loading setup. And the one nice thing here is that we're still going to be loading it on the second node, and we're still going to make the first and the third node to be fixed in space, and nothing really changes. So all we need to do is just to rerun it again under this new under this current configuration and see what happens, right? And by the way, the name we give for the self-folding and solver is the NR reconfigure ration. So after we rerun the simulation, this is the deformed configuration we get. So it does looks like because the bridge is now like covering a larger distance is becoming softer, right? So let's take a look at if that is indeed the case by taking a screenshot of these configuration and puts the previous configuration side by side for a quick comparison. Look at that, right? Indeed, the gray shape is the preloading configuration when the black shape is the loaded configuration. So although it's the same loading, in this longer, more skinny configuration, this deployable scissor mechanism is softer, right? We can see that the mid-span has a much larger deformation when we apply that -1 Newton of forces. So this is expected, right? For typically, if we still remember the knowledge we learned in the undergraduate mechanics class, when the beam, so basically this is a beam, right? When the beam is deep and the span is short, the deformation of the beam is gonna be small. But if the beam is very long and it's crossing a large distance and the beam is slender, that's where we typically see a very large deformation. So just like some sort of a paper deforming, papers are pretty soft because it's very thin. So this is kind of matching our expectations. And the one thing I would like to just briefly comment on is, as you can see here, what we are doing is we're running a single simulation to capture both the large kinematic shape morphing as well as that load carrying performance of this active structure. So that really highlights some of the advantages of using lump parameter models like these. So let's say if we want to model these system using the more traditional, say, a finite element with a frame or beam element, modeling this particular node here can be quite tricky. That's what I can tell you. And you typically might need to create some fictitious zero length elements to get that work. And it's not so straightforward. You cannot just directly release the moment connection here. That will make things that will not work very well here for the beam element. And also, when we are using that beam elements, the typical formulation we learned, let's say in our first finite element class covering the beam, or from the structure analysis class, let's say even for the 2D one, most likely they don't directly support large deformation that well. So when you rotate them into these larger configurations, like the one we're seeing here. So basically these deployment steps, they may not work very well because of the large deformation. So typically there are ways to make them work, but it will just requires you to get some more advanced formulation for that to really do that. But if you take a look at what we've been doing, right, with the lump parameter models, everything is captured, right? It automatically supports the large deformation, and that's one of the beauty of using it. And it really makes the solver and also the simulation so much easier to set up and faster to change things here and there. So that's just one of the final comment I hope to make about these examples. So next time, what we are going to be doing is to really go into the next theory sections. And what we hope to learn is how do we derive these 3-point rotational spring elements. So basically these particular element here using, again, that central difference method. So this is actually going to be very exciting because I would hope to show you that central difference is quite widely applicable to many different element formulations. And this time it would be these 3-point rotational spring systems. And with that, I would like to really thank you very much for your attention. And I really look forward to meeting you again in our next video tutorial in the section 10 next time. So have a great rest of your day, everyone.